Okay, so today I want to continue from my last session about solid edge detection. Now, let's go. I want to explore the Canny Edge Detection Algorithm. So I always want to do I want to implement it and also understand it a little better. So this is a good opportunity for me. So I have already. It took me around 2 hours. So I think I have somehow gotten it. So I will go through the code and also the algorithm in a bit. So Canny edge detection is a multi-stage algorithm to detect edges. So it is similar to Sobel, that in a sense it's used to detect edges in a digital images, and it shares common step with the Sobel edge detection, but it has some additional steps. So it was first proposed by John F. Canny, I think Canny in 1986. So this is the paper, I guess. If you are someone that enjoys technical paper and you can read it, so it's a very classic paper. I think it is in it is listed in the 10 most important AI research papers. So in usually in digital image processing, this is a kind of very important paper by John F. Canny. So the paper is technical in a sense. You can read it maybe to grasp some of the fundamentals, but to implement it and get the basic algorithm, I think the Wikipedia article is much better. So now the Canny edge detection, it has around 4 steps or 5 steps. Yeah, I guess these are the processes. So the top 2 steps are exactly the same as what we did for Sobel edge detection. Being that first we apply a filter, in this case it's a Gaussian filter, to smooth the image and remove noise, redo the noise, because the Canny edge detection, it is affected by like a noise, like any edge detection algorithm. So we need this Gaussian filtering. And second, we need to find the intensity gradients. So this is exactly the same as the Sobel operator. So we can use, I guess there are different kind of operators. Last I used the Sobel operator, so I will continue to use the same, continue to use the Sobel operator, but there are different type of operators that you can use. These operators are the kernels that we convolute within the image to find the edges. So this exactly the same as the Sobel operator. But now that additional thing is in the Sobel operator, we were only concerned of finding the magnitude of the gradients, the x and the y gradients. But now we need also the direction of the gradient, where the gradient is pointing. This is important for the Canny algorithm. This is the third step. So we find the direction of the gradient using the gy and the y and x gradients using basic trigonometry, and we divide those directions, those theta values, angle values, into 3 groups. So basically we want the vertical gradients, horizontal gradients, and diagonal gradients, so 2 diagonal gradients. So this is important we use it in the third step, because in Canny, third step is basically a kind of non-maximum suppression. We perform non-maximum suppression to thin the edges. So if where is it? Yeah. So if you see, for example, the output of the Canny edge detection algorithm and compare it with the Sobel one, you see that the edges are thinner, because this one is very noisy. So a lot of non-edge information here, the dark pixels. So it resembles more the input image than the edge image. But here, if you can see, the edges are clearly identified. The neighboring pixels are suppressed. So we need those directions. That is what this does. So after we find the direction, so we check for a particular pixel, for example, we have its magnitude. its value, intensity value, and its direction, where the change, this intensity change, is pointing. So what we do, and we, based on the direction, so we have the horizontal gradient, vertical gradient, and diagonal. So let's say, assume if a pixel is a particular pixel with some magnitude has a gradient direction that's vertical, then we will check its neighboring pixels. So in this case, it has 8 neighboring pixels. We'll take the 2 vertical pixels because they are on in the gradient direction, and we check the value with the intensity value of that pixel with the 2 vertical neighbors. So if that, because all of them are pointing on the same gradient, on the same line, what we do is, if the magnitude value of that pixel is, let's say, less than one of those pixels, we'll suppress it. So in that case, what happens is the edges become thinner. So it will be the edge will be well defined. So this is the edge thinning or non-maximum suppression step. And then after that, we do a double thresholding. So this same steps. So now, lastly, what we do. So here I was called noise color talk on this. High low threshold values if the edge curls. Yeah. Okay. So yeah. So what happens is, after this step, after we suppress a pixel by comparing it to its neighbors in the direction of its gradients, we also will, in the Canny algorithm, we provide 2 values, like defined values, lower and upper threshold values, and based on these upper and threshold values, we compare each pixel. So that pixel, we compare it with the upper and lower threshold value, and if it is, for example, its intensity value is greater than or equal to the upper threshold value, that means that pixel is a strong edge candidate. So we categorize them into 3 power based on their power. Like so we have a strong pixel, weak pixel, and suppressed pixel. So after we compare with each neighboring pixels, so let's say what we do is we group the individual pixels into 3 categories. So strong pixels will be the one that are visible. They are strong candidates for the edge, and the weak ones have they are between they are greater than the lower threshold value, but have intensity values less than the upper threshold value. So we will put those candidate values, and any intensity values below the lower threshold will be suppressed. Now, finally, the edge tracking, this edge tracking by hysteresis is to decide the fate of the weak edge values. So what we do, so for each weak pixel, we check its 8 neighbors, and if it has one neighbor that is a strong pixel, then we can consider that weak pixel to be a strong pixel. So its candidacy will be upgraded, and also now it can be used to decide the fate of its other neighboring pixels. So this is my overall understanding. Now, when we go to the implementation step, now I will try to go as much as I can. So this is the same step I implemented last time. So because for I don't think it's necessary for Canny Edge detection, but since we will be performing a Sobel operator, we need to convert the image to grayscale. So this step is just converting the image to grayscale. Like last time, I'll be using raylib. So to load the images and getting the raw pixel values, I used the raylib API. So for example, I load the image here using the load image functionality from raylib. So the image we have the image struct. It will have the data, which is the pixels, and the width, the height, and the format for the image, all these values. Then to get the pixels, the pixel values, that means these data values, we can use the load image colors, that is already defined function in the raylib API. Then after that, I can use my grayscale conversion. So we can convert the image to grayscale using this formula. Yeah. So then the second step in the Canny Edge Detection is the Gaussian blurring. So for Gaussian blurring, for example, in the Wikipedia, they are using a 5x5 Gaussian filter, but in my case, I just use a 3x3 Gaussian filter. So these values, I just use NumPy, maybe if you know, to generate a Gaussian values for a 3x3 matrix and just copy them. But this can be anything. But because when you generate a Gaussian distribution, so you can control the number using these values, standard deviation. So for this case, I just use some random standard deviation value and generated a 3x3 Gaussian distribution, so a matrix. So basically, after what we do after getting this Gaussian matrix is we just perform a convolution. That's the last step when we are doing Sobel operator. So we have this filter and we convolute that filter with the image, with that particular image, and then we find this blurred image intensity value and I return it. So that's the step. Now third step will be the performing Sobel operator, so the edge detection, but in this case it's different from the Sobel operator because we need the theta value also. So this is exactly the same. So this is the Sobel operator. So this is the Sobel operator for x and y. Now again we perform a convolution with the Sobel operator for the x and the y directions to find the x and y gradients for a given pixel. So for example, this is a given pixel. Then also for that pixel we can calculate the theta, the angle theta, using A2F function in C, in maths library. And after that we group the pixel into 4 gradient directions. We group them. So if you see the Wikipedia article here, so we can group them into 4. So these yellows are the same group. So any angle between 0 and 22.2. So between 0 and 22.5 degrees, and any angle between 175 and 180 degrees will map to 0. So this means like horizontal gradient. And so in the code, so any theta between 22.5 and 67.5 will be a okay, so will be a diagonal. Then okay, no, sorry, this is horizontal. Sorry, will be horizontal because we have 2 horizontals, and between 67.5 and 112 will be a vertical. So we have a horizontal and we have a diagonal. So we have 2 diagonal values. Okay. No, this was correct. Yeah. So this is the right diagonal. This one between 22.5 and 67.5. And we have a vertical between 67.5, this angle, and between 112.5 around here, and left diagonal between 112 and 157. So any remaining angle here and this one will be horizontal. So that's what we do. So for that, for holding the gradient direction, I created another struct. So first we have two enums. The first enum is the gradient direction enum. So we have horizontal, vertical, left diagonal, right diagonal. And second enum is we will see it later, is for the pixel power. So is it a strong candidate for to be an edge? Is it a weak, or is it suppressed? That will hold this H power enum. It will hold that information. Then what I did is I created a struct. So this struct will have these two informations. So for each pixel, I will be storing its gradient direction and its edge power. So that's what I did here in detecting edge. So I have already the magnitude, intensity values in these pixels, and this pixel grad array, which is the same size with the pixels. So we have image width by image height pixels. So for each pixels, we'll have a pixel grad, this struct that holds these two informations. So what I did is, in that struct for that pixel, I updated its gradient direction based on these conditions. So it is either diagonal, vertical, and so on. So this is the magnitude, which is the same as for the Sobel. So we update the magnitude. We take the square root of the squares of the two gradients, x and y gradients. Now after that, we perform this step, which is this step. So this step, I stored the directions, and based on the directions, now we compare the magnitude with the upper and lower threshold value. So these values will be defined. Let's say in my case, I define them in compile time. So these are the values, define lower and upper intensity values. So in my case, I just set my upper. So this determines the output. So the final output you can control based on these threshold values. So what we do is we train the candidacy for the edge. So if it is greater than its magnitude is greater than the upper threshold, it is a strong candidate to be an edge. If it is between the lower and the upper threshold, it is a strong candidate. It's like a weak candidate. And if it is intensity is less than the lower threshold, then we'll suppress it. That pixel will not be basically its value will be 0. Intensity value will be 0. Okay, so this is just like a helper function, just to set pixels and repeatedly writing it here. After that, we have the non-maximum suppression. Maybe I'm not sure if I change these orders, but okay, I will see. So in non-maximum suppression, what we do, we have the pixel. Now again, for each pixel, we will check it 8. So this is not 9, it's 8 neighbors. We will look through its 8 neighbors. Okay, so each pixel will have 8 neighbors in a square. Then what we do, first we check that pixel that we want and its neighbor, and we'll see if they are on the same direction, if they have the same gradient direction. Okay, so it has 8 pixels. Each pixels have their own gradient directions, and from those 8 neighboring pixels for that particular pixel that we want, we'll see if a pixel has the same gradient direction. So if it has the same gradient direction, then we can compare its value. So what we do after that, we compare its intensity value with its neighbor that had the same gradient direction. So for the particular pixel that we are checking, if its intensity value is less than its neighbor with the same gradient value, then we will suppress that pixel. Okay, the particular pixel that you want. So we will set its intensity value to 0. In my case, I'm setting its intensity value to 0, and also changing its that pixel's the power value in the struct to suppressed. So we do this for each pixel. This is the fourth step. Now in the fifth step, edge tracking hysteresis. That means in this one we will be trying to update the value for the weak. Okay, we have strong candidates, we have suppressed candidates. Those values we know. So the strong ones will be present. They are a strong candidate to be an edge. They will be present in the edge image. The suppressed one, their intensity value will be 0. They are rejected. But the weak ones, so they still have information. Some of them are like noise, but some of them could be like a good candidate to be an edge. So we have to basically decide their fate. So we use this edge tracking hysteresis step. That's what it does. So again, we will check for a pixel. We'll check its 8 neighbors. Then, but that pixel has to be weak. So for a pixel that is weak, we'll check its 8 neighbors, and if one of its neighbors is a strong candidate, then we can change that pixel's power value or candidacy value from weak to strong. So now what happens is this pixel was previously it was a weak candidate. It's now since it has a neighbor that's like a strong candidate to be an edge, we change it to a strong candidate also. Now then this pixel can be used to decide the fate of other pixels in the image. So this is basically the steps. So I will be sharing the code on GitHub and try to check for some bugs. But for now, everything works. I have checked it. Let's try it. And the image. So make. So let's say Canny, and let's give it the image. Yeah. So this is the Canny Edge Detection. You might see implementation. So if you can see here, let me go to the top and change the upper and lower intensity. So the final output depends. So if I say the upper to 100, lower to 20, and compile again. Yeah, see now, since I increased the upper threshold, so a lot of pixels will be either suppressed. Most of them are suppressed. So if you can see the output, so when I increase the upper threshold, I will be suppressing. So only strong candidates are left. So if you let it, for example, if you reduce this to 40 and this to 10. Yeah, now a lot of the pixels will be also strong candidates. So this is basically my implementation. I'm sure. So this is my version. I just read the Wikipedia article and try. I did not consider any sources for now because I want to see if I could try to approximate it. I have seen the outputs. So here, could I? Yeah. In the outputs, the edges seem to be connected, but in my case, they are kind of. I don't know how to zoom this. So there is a discontinuity. Yeah. So most probably there's. I think I have missed some step, or like I have exchanged some orders, computational orders, which I'm not sure. But for me, this is actually good approximation. So I've learned a lot of things from this, and I hope you you learn also from the code some basic idea of how this algorithm works, uh, and you can try to implement it. So I'll be sharing in my GitHub the link to this project on the description or in the comment on the YouTube video, so you can clone it or contribute to it. And also, if you have better results, you can comment and share your codes. So that's it. Thank you very much. Bye.